Good evening, everybody. I welcome you all to the 10th week of live interaction sessions for the course Bioinformatics Algorithms and Applications. So, the live session for this week was held on 7th of April, Friday at 6 p.m. as usual, but unfortunately, due to a technical glitch, my video was not recorded. So, therefore, this is going to be a quick recap of the questions discussed on Friday, and I will not be waiting for answers to drop in or be taking live responses from people. But this will be a quick solving session of the questions that were taken up this Friday. And I will also be attaching the audio after this quick session so that you can have use that to practice with the PPT for a more uh, interactive or a session that allows you to take time, solve, and get back with the answers. Okay, let's start. So, this week the practice questions focus on computer aided drug design part 2, virtual screening parts 1 and 2, and quantitative structure activity relationship parts 1 and 2. First question, a rather simple and straightforward one. Drugs are approved by option A FAD, B FDD, C FDA, and D FAAD. So I'm going to jump right into the answer. Answer is option C, FDA, Food and Drug Administration, and this is applicable to US standards, which strictly monitors the food products and drugs that are deemed safe for the people to consume. Question 2. Which of the following is not a docking program? Option A, Autodock, B, Glide, C, Bio 3D, and D, Gold. So we all know that Autodock is a docking program, so this cannot be our answer. And so is Glide and Gold. I have a few snips here to help us. So Glide is the snap of the website, a complete solution for ligand receptor docking. And similarly, you have Gold as a validated configurable protein ligand docking software for expert drug discovery and lead optimization, right? So, and we all know Autodock is a docking program, so that leaves Bio 3D, which is an R package containing utilities for the analysis of protein structure, sequence, and trajectory data. So there's no docking service available with Bio 3D. The right answer is option C. Question 3. Which of the following statements about QSAR is correct? QSAR can be utilized to identify and optimize leads. It can predict admit properties, and C, multiple regression method is used in QSAR. So QSAR obviously is used to identify and optimize leads, which is true, and it can also predict admit properties because if you did not pay attention to admit, which is absorption, distribution, metabolism, excretion, and toxicity of lead compounds, then you cannot arrive at a successful drug. So it has to predict admit properties and it has to be within the acceptable limits or the optimal range for a lead compound. And definitely multiple regression is used in QSAR. Therefore, the right answer is option D, all of the above. Question 4. If the concept of lock and key is considered in molecular docking, protein ligand interactions, the lock and key are respectively, the clue is right here, in protein ligand interactions, molecular docking. If the concept of lock and key is considered, What would the lock and key be? Option A, ligand and protein. B, protein and target. C, protein and ligand. And D, ligand and molecule. So, as the question indirectly suggests, and which is the lock here, and the larger protein molecule, and where the activator or inhibitor, the ligand molecule, is the key which is trying to fit into the lock. Okay, so it's protein and ligand. Option C is the right answer. Question 5. Which of the following databases contains small molecules? Option A, zinc and CHEMBL. Option B, PDB and zinc. Option C, DDBJ and PDB. Option D, zinc and thrombin. So we know that these are sequence based databases. PDB is structure database, although not of small molecules specifically. So they might be found in complexes with protein, but not it's not a database containing small molecules. So that leaves zinc and Campbell as the options, right? So this is wrong and option A is right. So I have a description here. It's a free database of commercially available compounds for virtual screening. Contains over 230 million purchasable compounds in ready to dock 3D formats. It also contains over 750 million purchasable compounds. You can search for analogs in under a minute. CHEMBL is a manually curated database of bioactive molecules with drug like properties. It brings together chemical, bioactivity, and genomic data to aid the translation of genomic information into effective new drugs. So it also has disease specific category for malaria. So a lot of information can be found in these databases for finding small molecules. Question 6. Which of the following is the search algorithm used in docking? Option A, simulated annealing. B, torsion angle. C, Wunsch-Needleman. And D, Smith-Waterman. To start with, torsion angle is not an algorithm, so you can check the option right away. Wunsch, Needleman, and Smith Waterman are sequence alignment algorithms, right? Whether it is local or global. So the only algorithm that is used for searching and docking amongst the given options is simulated annealing. Option A is right. Which of the following are measurable molecular descriptors? Is it refractive index, polarizability, surface area, or all of the above? So, amongst molecular descriptors, we have two categories. Those that are measurable and those that are calculated. So amongst measurable properties, you have descriptors. You have density, pKa, ionization potential, refractive index, dipole moment, and under calculated descriptors, molecular descriptors, you have surface area, molecular volume, polarizability, so you have surface area and polarizability here, which are part of calculated. You have refractive index, which is measurable and it's not all of the above. You also have molar reflectivity and so on. Okay, question 8. Which of the following is not a major component of force field based docking scoring? A. Van der Waals, B. Electrostatic, C. Covalent interactions, and D. None of the above. Not a major component of. So, force field scoring uses the equation summation of so amongst these, the first part is to do with van der Waals, force of attraction and repulsion. The other part concerns the electrostatic component. So, under not a major component, both these will fail, and none of the above can also not be true. The right answer is covalent interactions is not a major component of force field based docking scoring. Question 9. The IC50 values of three protein ligand complexes are 6 nanometers, 7 nanometers, I'm sorry, 6 nanomolar, 7 nanomolar, and 4 nanomolar. The IC50 values are related with a combination of hydrogen bond donors as 232 respectively, hydrogen bond acceptors 344 respectively, and polar surface area 1, 2, and 3 respectively. The IC50 value of a compound with 3 hydrogen bond donors, 3 hydrogen bond acceptors, and a polar surface area of 2 is dash nanomolar. So, on one hand, we have a measurable property of protein ligand complex, which is IC50, and it is a function of three components as we see here. And what are those? Hydrogen bond donors, which I'm writing as HBD, and hydrogen bond acceptors, which is HBA, and polar surface area, which I'm writing it as PSA. So there's going to be a coefficient for each of these components that IC50 depends on. So I'm going to name those coefficients as X, Y, and Z. Now let's write the given information here. So we have 6 nanomolar, 7 nanomolar, and 4 nanomolar as the three cases wherein the IC50 values are related to the combination of hydrogen bond donors, which is HBD, as 2, 3, and 2 respectively, and these go with the coefficient X, and hydrogen bond acceptor as 3, 4, and 4 respectively. And finally, polar surface area of 1, 2, and 3 respectively. Now you have to see each of these equations as a combination of three components. So 6 nanomolar of IC50 is obtained when you have this equation of 2x plus 3y plus 1z. Similarly, you have all three components, hydrogen bond donor, acceptor, and polar surface area, contributing to a 7 nanomolar IC50. Alright, so you have three variables and three equations, therefore it is easily solvable, right? So I'm going to use my calculator to enter these values. I'm going to use a different color so it's easy on the eyes and more visible. So we'll be using a matrix to solve. So I'm writing the values for hydrogen bond donor, acceptor, and polar surface area here. And we have it has to be 3 cross 1, right, in order to get 3 cross 1 again. So this is 6, 7, and 4. right? So let's solve for this. For those who are not familiar with solving equations by calculator, so you can use the mode button in your scientific calculator and keep pressing it until you arrive at the option equation. And there are two ways of operating, one with unknowns, the other with the degree of polynomial. So here we have three equations and three unknowns rather than uh, polynomial of degree 3 or equation such. So we're going to go with unknowns and 3. So it'll start with asking you what is A1. So it will be like A1, B1, C1, A2, B2, C2, A3, B3, C3. Some calculators might have it or display in matrix format already. You'll have D1, D2, and D3. So this is how we are going to enter the values as well. So A1 would be 2, B1 will be 3, C1 is 1, D1 is 6, A2 is 3, B2 is 4, C2 is 2, D2 is 7, A3 is 2, B3 is 4, C3 is 3, and D3 is 4. So which gives me the answer x is equal to 1, y is equal to 2, and z is equal to minus 2. So these are my coefficients that we have found by regression. Now the question asks the IC50 value of a compound with 3 hydrogen bond donors. So HBD will be X. 3X plus 3 hydrogen bond acceptors, 3Y, plus, and a polar surface area of 2Z is equal to what? So now that we know the answers to x, y, and z, can't we? I mean, we can substitute and find the answer, right? So 3 into 1 plus 3 into 2 plus 2 into minus 2. That is 3 plus 6 minus 4. We'll check the answer. So that's right. We have 5 nanomolar as the answer. Question 10. Which of the following depends on empirical based scoring function? A. Autodoc, B. Gold, C. Glide, and D. PMF. So PMF we know is a knowledge based scoring function. Glide, on the other hand, is an empirical based scoring function. Orthodox and gold, on the other hand, are force field based scoring function. Therefore, for the question of which is empirical based, Glide is the answer. With that, we move into the current year's assignment for week 10, which most of you would have solved and submitted by now. Question 11. 2D QSAR deals with option A molecular properties, option B connectivity indices, option C surrounding atoms in the structure, and D all of the above. So amongst QSAR we have, so these were the ones discussed in lectures. So these models of QSAR are classified based on uh, how the structure, based on the structural representation and the method used for deriving descriptive values. So 1D QSAR correlates activity with global molecular properties such as pKa and log P values. So I'm going to write global molecular properties. Just the keywords are ready reckoners here. 2D of course considers the connectivity indices. 3D also includes interaction fields from surrounding molecules. And 4 also includes the ensemble of ligand configurations. 5D representing different induced fit models. I'm just going to write induced fit models. And 6D including different solvation models. Current question 2D QSAR deals with connectivity indices. Question 12. In protein ligand docking, two important bottlenecks are A. Binding site prediction and conformational sampling, B. Conformational sampling and scoring function, C. Binding site prediction and scoring function, and D. None of the above. So the two main components of docking would be the search algorithm and scoring function. Where search algorithm comes up with, generates a large number of poses of a molecule in the binding site, while scoring function calculates a score or binding affinity for a particular pose, right? So it has nothing to do with binding site prediction, which moves A, C out of the equation and also D. With conformational sampling, which is again a search algorithm and scoring function, fit the bill. Therefore, B is the right answer. In protein ligand docking, the two important bottlenecks are conformational sampling and scoring function. QSAR involves the following steps: construction of model, generation of descriptors, collection of ligands with experimentally known activity, validation of model, and feature selection. Choose the correct order. So the process involves collection of ligands, generating their descriptors, feature selection, constructing a model, and validating a model. So from a rough idea, we know that the final step is the validation of a model. So 4 would be the end. You will not validate a model and then feature select, or you will not validate the model and then do all the other steps. So therefore B and D can be removed. So amongst these two options, when you logically see, or if you're aware of the right process of QSAR, anybody would know that the first step is the collection of ligands with experimentally known activity. Second would be generation of descriptors, molecular descriptors, and three would be feature selection or further filtering those molecular descriptors, and four would be to construct a model based on these, and five to validate that model which has been generated. So it would be 3, 2, 5, 1, and 4. That's option C. Question 14. Which of the following uses a force field based scoring function? Autodoc, ChemScore, Glide, or TMS? Once again, we know that ChemScore and Glide are empirical based scoring function. EMF, on the other hand, is a knowledge based scoring function. Autodoc is the only force field based scoring function. Option A is right. Genetic algorithm is a option A is systematic search, B stochastic search, D greedy incremental search, and D dynamic search. So amongst the kinds of search in flexible docking, stochastic search was described in detail, which included simulated annealing, genetic algorithm, amongst others, such as taboo search, hybrid global local search, and Lamarckian genetic algorithm. So, the answer for this question, genetic algorithm, is a stochastic search and not A, C, or D. Question 16. Chemical complementarity score mainly depends on hydrogen bond donors and acceptors at protein site, hydrogen bond donor and acceptors at ligand site, hydrogen bond donors and acceptors at protein and ligand sites. D charged atoms. The scoring function, which uses shape and chemical complementarity, works by dividing the accessible protein surface into zones, namely hydrophobic, hydrogen bond accepting and hydrogen bond donors. And similarly, dividing the accessible ligand surface into zones of these three regions. So put together, it will be protein and ligand sites. Therefore, option C is the right answer. Question 17, another similar question. IC50 values of three protein ligand complexes are 6 nanomolar, 15 nanomolar, and 2 nanomolar, where IC50 is a function of hydrogen bond donor, hydrogen bond acceptor, and polar surface area, which are going to be named as X, Y, and Z. So these are given by 3, 2, and 1. Hydrogen bond acceptors of 5, 6, and 5. And polar surface area of 4, 1, and 2. So the regression coefficient of hydrogen bond donor is, so HBD is, has the coefficient of X. So the question is all about what is the value of X. So we'll be solving as usual 3, 5, excuse the color. So I'm going to use my calculator again. A1 is 3, B1 is 5, C1 is 4, and D1 is 6. A2 is 2, B2 is 6, C2 is 1, D2 is 15. A3 is 1, A2 is, sorry, B2, A3 is 1, B3 is 5, C3 is 2, and D3 is 2 again. So which gives us x is equal to 7, y is equal to 1, and z is equal to -5. So IC50 is given by 7x plus y minus 5z. And to answer the question here, the regression coefficient of hydrogen bond donor X is 7. Let's check the answer. That's right. 7. For the data given in question 17, the IC50 value of a compound with 2 hydrogen bond donors, 4 hydrogen bond acceptors. I'm sorry, I shouldn't have written. These are the values for X. y and z. Therefore, let me rephrase, rewrite this equation. So IC50 will be 7 into say A plus B minus 5 into C, where A is the value for hydrogen bond donor, B is the value for hydrogen bond acceptor, and C is the value of polar surface area. So you have polar surface area of 3. So these are A, B, and C respectively, and what is IC50, which is 7A plus B minus 5C. 7A would be 2 plus B is 4 minus 5 into 3. 7 twos are 14 plus 4 minus 15. That will be 4 minus 1, which is 3. Let's check the answer. It's right. We have 3 nanomolar as the right answer. Question 19. The binding affinity of a protein ligand complex is estimated using search space, search algorithm, scoring function, and D virtual screening. So the answer is definitely scoring function, right? The binding affinity. Scoring functions are often to determine how the affinity in case of different complexes or which is better. It cannot be estimated using a search space or a search algorithm or virtual screening, but a scoring function which helps estimate the binding affinity of a protein ligand complex. So, straightforward option C. Question 20. Percentage of test data points in a jackknife test is A 100%, B 99%, C 70%, and D 33.3%. So the jackknife test discussed during the lectures was with excluding one data for prediction or test and using all the other data n minus 1 data used for training, which forms the training data set, and the left out one data is used as test or to make prediction. This is done n times. So for example, if I have data of, let's say, So I'm going to, so each time four of these are going to be used. It could be any four. So you can have 3.62, 3.97, 3.15, 3.83 as test set for the first time, and using and sorry, for the training set you're using four data points, and using the last one for making prediction, the test data set, right? Similarly, for the second case, if I were to use, I'm just trying to create a visual. All right, so in each case we are using four different data. So if n is equal to 5, n minus 1 is equal to 4. Therefore, in first case we used first and last three data as training, and the second one as test. In second, we use first two and last two as training, and third as the test to make the prediction based on how the model is trained with the other four data points. And in third case, so these are n times or 5 times, right? The first data set is the test, and last four are training. So we have covered first as well. And then fourth case, it's the fourth one, which is test, and fifth is the fifth data point. So all of 1, 2, 3, 4, 5 points in the data have been used as test data points. Therefore, when you do a jackknife test with n minus 1 data as the training set and one data point as the test to make a prediction, and repeat for n times, the percentage of test data points will be 100%. I have a couple more questions. Comparison of physico-chemical properties with known active compounds could reduce the initial data set to 50% or less, 95%, 90%, and 85%. So, comparison of physico-chemical properties with known active compounds is going to filter the initial data set much better than 85, 90, or 95%, and therefore it should be 50% or less ideally. So, option A is right. Question 22. If the Pearson's correlation coefficient between the two sets of data is 0, then option A, no correlation, B, positive correlation, C, random relationship, and D, negative correlation. If it's 0, so R ranges between -1, 0, +1. Excuse the color. Okay, -1 is for negative correlation. This is no correlation, and this will be positive correlation. Don't mind there's a change in the question. Answer for 0 is no correlation. Question 23. Choose the application of docking scores. Is it A, to fix a particular position of the ligand, B, to reduce the degrees of freedom, C, to rank the active compounds, or D, all of the above? The application of docking scores would not be to fix a particular position in the ligand. That's wrong. And not to reduce the degrees of freedom, but rather to rank the active compounds. Not all of the above either. Alright, with that, I've completed the questions I have for this week, and I hope to see you all next week as well at 6 p.m. on Friday. Thank you very much. I'll be uh, joining the audio version of the real life session along with this in case you would like to use the PPTs to slowly go over the answers. Thank you.